Hello everyone, and welcome to our channel, MooTechie. This deck is all about enzyme kinetics and enzyme inhibition. We've got a very visual presentation for you, packed with curves, plots, and mechanisms. We'll have a clean layout with colored keywords and some subtle animations. Now, let's move on to our introduction to enzyme kinetics. Enzymes are biological catalysts. They speed up reactions without being consumed themselves. We study their reaction rates and the factors that affect them, like pH, temperature, and substrate concentration. The core pathway is E plus S in equilibrium with ES, which then produces E plus P. Our focus metrics are Km and Vmax, which are measured from initial rates. On this slide, we also see a plot of reaction rate, labeled V, against substrate concentration, labeled A. It shows a classic hyperbolic curve. The reaction rate equation is shown. V equals Vmax times the concentration of S divided by Km plus the concentration of S. The curve starts at 0, rises steeply, and begins to plateau. A point is marked at half of the maximum velocity, V, and this corresponds to the substrate concentration value, Km, on the x-axis. Next, we explore the Michaelis-Menten equation basics. The equation is V equals Vmax times the concentration of S divided by Km plus the concentration of S. This assumes a steady-state concentration of the ES complex, and we analyze the initial velocity, V0. At low substrate concentration, we see first-order kinetics, where the rate is proportional to substrate concentration. At high substrate concentration, we see zero-order kinetics, where the rate is independent of substrate concentration. Visually, we have the Michaelis-Menten curve with markers for Vmax and Km. The graph on the slide shows velocity on the y-axis and substrate concentration in millimolar on the x-axis. The curve rises and plateaus, with a dashed line marking the maximum velocity, Vmax, and another marking the substrate concentration at half Vmax, which is Km. Coming up, let's understand Km and Vmax more deeply. Km is the substrate concentration at half Vmax. A lower Km means a higher enzyme affinity for the substrate. Vmax is the maximum rate when all active sites are saturated. It depends on the total enzyme concentration. kcat is the turnover number, calculated as Vmax divided by the total enzyme concentration. We can estimate these values from the curve or from Lineweaver Burk plot fits. The slide also has a simple figure of a reaction curve showing Vmax, half of Vmax, and the corresponding Km on the substrate concentration axis. Next, we explore the Michaelis-Menten curve visually. The curve has distinct regions. It's linear at low substrate concentrations and forms a plateau at saturation. It shows a hyperbolic relationship between velocity and substrate concentration. A large plot is visualized with callouts, marking Km at the point of half Vmax. The curve clearly shows how velocity increases with substrate concentration until it can go no faster. Now, let's discuss the Lineweaver-Burk plot. The equation is 1 over V equals Km over Vmax times 1 over the substrate concentration plus 1 over Vmax. This is a double reciprocal plot. 1 over V plotted against 1 over the substrate concentration. The y-intercept equals 1 over Vmax. The x-intercept equals negative 1 over Km. These straight lines help us classify different inhibition patterns. A word of caution: this plot can weight errors unevenly, so nonlinear fits are often preferred. The diagram on the slide shows 3 lines on a graph of 1 over velocity versus 1 over substrate concentration in inverse millimolar. The lines represent no inhibitor, competitive, and non-competitive scenarios intersecting at different points. As we continue, let's understand the landscape of enzyme inhibition. We're looking at different mechanisms of enzyme regulation. First, reversible inhibition. Competitive inhibition binds the active site, affecting Km but not Vmax. Non-competitive inhibition binds an allosteric site, affecting Vmax but not Km. Uncompetitive inhibition binds the ES complex only, affecting both Km and Vmax. Then there's mixed inhibition. This binds both E and ES with different affinities, affecting Vmax and variably affecting Km. Then there's irreversible inhibition. This is covalent or time-dependent, leading to permanent inactivation where the off rate is essentially 0. The apparent Vmax decreases over time. We can observe the effects of inhibitors through shifts in Km and/or Vmax, which are analyzed using Lineweaver Burk plots. Moving forward, let's see competitive inhibition in detail. The inhibitor binds only the free enzyme E and is mutually exclusive with the substrate S. This causes Km to increase while Vmax remains unchanged. On a Michaelis-Menten curve, the curve shifts to the right. On a Lineweaver Burk plot, the lines share the same y-intercept. This inhibition can be overcome by increasing the substrate concentration, as they compete for the same active site. The slide includes a diagram showing active site competition between a substrate S and an inhibitor I. It shows a free enzyme, an enzyme substrate complex that is productive, and an enzyme inhibitor complex that is blocked. A graph compares the Michaelis-Menten curves for no inhibitor and with a competitive inhibitor, showing the latter curve shifted rightward. Let us now look at noncompetitive inhibition. Here the inhibitor binds both E and the ES complex at an allosteric site, a site different from the active site. This causes Vmax to decrease while Km remains unchanged. On a Michaelis-Menten plot, the plateau is lower. On a Lineweaver Burk plot, the lines share the same x-intercept. This type of inhibition cannot be overcome by increasing substrate concentration. It reduces the overall catalytic efficiency. The slide has an illustration showing an enzyme with an active site and a separate allosteric site where the inhibitor binds. A graph shows Lineweaver Burk lines for no inhibitor and noncompetitive inhibition intersecting on the x-axis. Next, we explore uncompetitive inhibition. This inhibitor binds only the ES complex, which actually stabilizes it. Both Km and Vmax decrease together. On a Lineweaver Burk plot, this results in parallel lines. This inhibition becomes more effective at high substrate concentrations. A key point is it cannot bind the free enzyme, making it a unique mechanism. The slide shows a simple diagram indicating no binding to free E, only to the ES complex. A Lineweaver Burk plot shows parallel lines for no inhibitor and uncompetitive inhibition. Now, let's understand mixed inhibition. The inhibitor binds both E and ES, but at different sites and with different affinities. Vmax always decreases. Km can either increase or decrease depending on a constant alpha. On a Lineweaver Burk plot, the lines intersect to the left of the y-axis at a negative x-intercept value. A special case is when alpha equals 1, which is identical to noncompetitive inhibition. If alpha is greater than 1, it appears more competitive-like. The slide includes a small graph showing lines for no inhibitor and mixed inhibitor intersecting in the left quadrant. Coming up, we discuss irreversible inhibition. This involves covalent or extremely tight binding with essentially no release of the inhibitor. It permanently inactivates the enzyme's active sites. We see an apparent decrease in Vmax over time as activity is lost time-dependently. This type of inhibition cannot be reversed by dialysis or dilution. Examples include aspirin, penicillin, and organophosphates. The slide has an image illustrating time-dependent activity loss. A graph plots enzyme activity in percent against time in minutes, showing a curve that starts at 100% and decays downward over time. To bring it all together, let's summarize the Km and Vmax changes by inhibitor type. For competitive inhibition, Km increases, Vmax is unchanged. The Lineweaver Burk pattern shows lines with the same y-intercept. For non-competitive inhibition, Km is unchanged, Vmax decreases, the lines intersect on the x-axis. For uncompetitive inhibition, both Km and Vmax decrease, the lines are parallel. For mixed inhibition, Vmax decreases and Km effect is variable depending on alpha. Lines intersect left of the y-axis. For irreversible inhibition, Km is unchanged, Vmax decreases time-dependently, often appearing non-competitive. Thank you so much for joining me in this exploration of enzyme kinetics and inhibition. I hope it all makes a little more sense now. Remember to like, share, and subscribe to MooTechie. In our next episode, we'll delve into allosteric regulation and enzyme control. If you have any questions, feel free to contact us at hello@mootechie.com. Thank you. See you in the next class.